Hello and welcome to this presentation on the concept of decidability and undecidability. So today we'll explore these fundamental ideas in the field of theoretical computer science and discuss their significance in understanding which problems can and cannot be solved by an algorithm. Okay, so to begin, let's clarify the main questions. What does it mean for a problem to be decidable and undecidable? So we'll look at how these concepts are related to the computational theory, the Turing machines, if you are familiar with that, and the limitations of what computers can solve. Okay, so by the end of this presentation, of course, you'll have a better understanding of the key differences between decidable and undecidable problems. So along with the examples that demonstrates how these ideas apply in practice. Okay. Okay, so of course, in this presentation, we'll have a brief history about this undecidable and the decidable, and we have also an application in computer science and software engineering. Now, in theoretical computer science, decidability refers to problems that can be solved by an algorithm in a finite amount of time. So while undecidability pertains to problems which no such algorithm exists. So it means that decidability problem or a problem is solved in the undecidability, the problem is solvable by algorithm in a finite time. And while the undecidability is some problems have no algorithm to solve them. So you can mention how these are important in the field of automata theory and complexity theory. So as they help us understand what computers can and cannot do. So of course, in automata theory and complexity theory, they will help us to understand what computers can do or cannot do. Okay. Okay, so now we will go to the history of undecidable and undecidability. So the origins of decidability track back in the early 20th century, which the works of logicians such as David Hilbert and Kurt Gödel. So not only that, also the Alan Turing. So which having a Turing machine. So David Hilbert, so in the early 20th century, he posted that Enskidang's problem. So it means that if there was a way to determine the truth of every mathematical statement, so there's a way to determine the truth of every mathematical statement. While Kurt Gödel, so that is a 1931, he showed with his incompleteness the theorems that some truth in mathematics cannot be proven, of course. So revealing limitations in formal systems. So that is the Kurt Gödel. And Alan Turing is he expanded the Gödel's work by proving the halting problem is undecidable. So Turing showed that no algorithm could decide whether a program will halt or run forever. So these works laid the foundation of the computability theory. So it means that in the 20th century, we have David Hilbert and Kurt Gödel's, also Alan Turing, which is Alan Turing is he expanded on Gödel's work, which is in it has an incompleteness from Gödel's. Okay. Okay, so next is it has an application in computer science and software engineering. So number one, halting problem. So what is this halting problem? So Turing halting problems demonstrate that it has a right program that can determine for every statement together. So halting problem explain how the halting problem demonstrates and undecidability. So We cannot write a program that predicts for every other program whether it will stop or keep running. So that is the halting problem. So the second one is automated theorem proving. So in formal verification and logic-based systems, decidability plays a key role in determining which propositions can be automatically proven by algorithm. So automated theorem proving that I mentioned that algorithm can automatically prove in simple propositions. It means decidable. So, but more complex in logic. Like first order logic becomes undecidable. So it is like that. And then the impacts areas like formal verification. So that is an automated theorem proving. Okay, next is the type checking. So type checking in programming languages, certain type systems, they are designed to be decidable. So it means that some programming languages have a simple or decidable type systems that catch errors, of course, before a program runs. So there is some programming languages that the developer will encode the program, it will shows the error. So it means that you can decide, or that is decidable. So more complex type systems might not catch all errors. So of course, if the statements or the system is complex, so there is a lot of errors, and that is an undecidable. So making them undecidable, so if the system is more in complex, so that is a type checking. Next is the model checking. In software engineering, model checking is a technique for verifying finite state uh, system. So while many problems in model checking are decidable, more complex system, particularly those involving infinite states, may become undecidable. So it means that uh, model checking in finite state systems, model checking is decidable. Why? However, can become undecidable because affecting software verification. So dyan lang po siya magiging undecidable. Okay, next is formal languages. So, formal languages, decidability is a significant aspect of formal language analysis, particularly as an indication of the discrimination between classes, regular, and context-free language. So, it means that there is a highlight there, the role of decidability. So, there is a role of decidability. Um, why is it called decidability, or there is a role in decidability? Because there is analyzing formal language, and regular and context free languages are decidable. So of course they are decidable, but more complex language might include undecidable elements. Gets, do you understand? Okay, so that is the applications in applying those one in computer science and in software engineering. So of course, decidability and undecidability provide deep insight into what can and cannot be computed. So while many practical problems in computer science are decidable. Okay, so uh, the summarize, or let's summarize about the decidability. So the decidability and undecidability help us to understand what can and cannot be computed. Most practical problems in computer science are decidable. So, but limits our ability to fully analyze of verify complex. This leads researchers to find workarounds like approximation or specialization methods to solve certain problems. Okay, so that's all for my presentation, and hope you can understand what is the decidable and undecidable. Okay, so thank you so much for watching. God bless us all.